Today we will cover actually only four major topic. This one here, I will mention it briefly. Now we will answer a big question. Therefore, so far we have learned the mean and standard deviation, mean and variance, and from variance we get standard deviation. Then what are the use of this? Oh, before I go too far, I would like you to realize that do not use the standard deviation formula from our textbook. Let's see. Give me a second, okay? I want to show you the textbook. I think that's in chapter 3. Huh? It should be in chapter 3. I don't like it this way. Why did I go to chapter 4? To chapter 3. Mm-hmm. Oh, that's chapter 4. Why it takes so long? Why it takes so long? This is chapter 4. Okay. It's chapter 3. It's supposed to be chapter 3 here. In our chapter 3, they actually use this strange formula. Why it's so slow? I should have just downloaded it. You know what? I opened it from my computer. Okay. Give me a second. Yeah, they use this formula here. This, you see, am I sharing it right now? Yeah, I'm sharing it right. So this is the definition formula. This is the definition formula for standard population standard deviation. However, when they use computation formula, they write it this way. They write it as a complex fractions inside the square root. And computationally, this little, I mean, it will still give us the correct answer though, okay? It still gives us the correct answer. Now you see, they don't really do the variance, they do the standard deviation right away. It does the square root right away. Okay, now the thing is this, you have complex fraction inside the radicals such that you have potentially two rounding errors instead of only one rounding error. Okay, and this is not the formula we commonly use in other textbooks. Even if you open Wikipedia, you will not see this formula. Okay, at least they will not write it that way. Okay, so to be honest with you, I don't understand why this book wants it this way. I'm not alone. I'm not alone. Trust me. I find it to be very strange that our textbook write it that way. Okay, so our textbook write the population standard deviation according to population standard deviation. So let me just use the notation. Our textbook write population standard deviation as the square root of the sum of x squared minus the sum of x being squared over n, big over n, but still inside the square root. Okay, now if you have learned algebra before, our formula actually basically multiply the top and the bottom by n. Now then you see this n here multiplied by these give us n times square root of x squared. Okay, and then when n is multiplied by this chunk here, you cancel the denominator, right? You cancel the denominator, so you end up with the square of the sum of x over the denominator. When you multiply by another n, you get n squared. Like that. Okay, now that's for their standard deviation. Now the way I define standard deviation, okay, which is actually most other textbook, we define standard deviation as the square root of variance. Now then, how to find the variance? Now my variance is basically what you see inside here. Okay? Okay, so I don't go to standard deviation right away. I go to variance first, and then from variance, I get to the standard deviation. Okay, now that's the formula for raw data. If you are given raw data, then that's the formula we use. Okay, well, anyway, let's go back further to our topic. So the first one is the uses of, I think I need to emphasize its early uses though. Early uses of mean and standard deviation. And the first one is Chebyshev. Chebyshev Theorem. That says the portion of the data I think I should say the portion of the population or sample that we are dealing with depends on what you have, more than k standard deviation away from the mean, is less than 1 over k squared. I know the wording is kind of tough, huh? The wording is kind of tough. Okay. Let's first understand what does it mean to say k standard deviation away from the mean. Okay. Now suppose I have this distribution here. Okay. And then suppose the mean mu. Now then we go 1 standard deviation away from the mean. So I add sigma and I subtract sigma here. Okay, and then do once more, let's say 2 times. So this guy here will be the mean plus twice standard deviation. And this is the mean minus twice standard deviation. Now, the data may be distributed in some strange way. Okay, doesn't matter. Okay, now, according to this Chebyshev theorem, it says that the portion of the data, the portion of that population, in this case is population because I use mean, I use mu, right? Then the portion of the data that is more than twice standard deviation away from the mean. This is the mean. Notice that this is the mean. Okay, so this is within twice standard deviation from the mean. While this part here more than twice standard deviation away from the mean. Now it is said that this part here, together with that part, okay, must be less than 1 over 2 squared of the data. In this case is population. Okay, now sometimes this Chebyshev theorem is this. Oh, I forgot one thing. In fact, that's super important. The k here has to be strictly greater than 1. It has to be strictly greater than 1. Okay, so suppose using the example we have earlier that when k equals to 2, then the portion of population more than twice, 2 standard deviation away from the mean, is less than 1/4. Okay, so at most 25% of the population, is outside of that twice standard deviation from the mean. Another way to say it, alternate way, the portion of population within twice standard deviation of the mean is more than 1 minus 1 over 2 squared, which is 1 minus 1/4, that's 3/4. Let's go back to this picture. Maybe the picture will help us to see the more concrete information. Now it says that according to Chebyshev, this blue part here, if I combine, is less than 1/4. This part here, this blue part here, is less than 1/4 of all the data. Now, if this is less than 1/4, then the one inside must be more than 3/4. Right? The one inside must be more than 3/4. That's more than 1 minus 1/4 of the population. Okay, try to imagine it this way. Okay, I hope I can illustrate that. So suppose we have 100%. Okay, and then if I say this is 25%, then this part here must be 75%. Is it right? Okay, now suppose I change this 25% to be less than 25%. Suppose I say this is 24%. Then what portion will this be? That will be 76%. Is it right? Okay, so in other words, the lesser this guy is, the more this guy be. Is it right? Okay. Now, then, if we see another case, let's say when k equals to 3, so 3 standard deviation away from the mean, then the portion of the population, within 3 standard deviation of the mean is more than the one inside, the one in the middle. It's more than 1 minus 1 over 3 squared, which is 1 minus 1/9. That's 8 over 9. Okay, so you can imagine, suppose I have the data. Okay, and this is the mean. I go 3 standard deviation to the right and 3 standard deviation to the left. Now then the portion in between, depends on the portion on the outside, right? According to Chebyshev, this guy here combined is less than 1/3 squared, which is less than 1/9. Right? Now it means the guy in the middle here must be more than the remaining. Okay, and it applies to every k greater than 1. So it doesn't have to be k equals to 2, k equals to 3. It is possible we have k equals to 1.5, and the same rules still apply. Okay, the same rules still apply. So let's apply this to a more concrete example. Suppose, for example, we know that the mean, it doesn't have to be population, but let me just use population for now. Let's say the mean is, let's say 64, and the standard deviation turns out to be, let's say 12. Now, using these informations, then we can ask the what portion of population is between let's see, 46 and 82. Now note that this 46 is 64 minus 1.5 times 12. And this 82 is 64 plus 1.5 times 12. If I try to picture that, the mean is 64. Okay, 46 is here, 82 is here. Okay, and then the standard deviation is 12. So it's 12 plus 6. Okay, and then from the mean, subtract by 12, subtract by 6. So you see that the distance here is actually 1.5 times standard deviation. 1.5 times standard deviation. Oh, if you want to know how I get that 1.5, you can do this way. 82 minus 64 divided by the standard deviation. That's 18 over 12, that's 1.5. Okay. 46 minus 64 over 12, that's negative 18 over 12, that's negative 1.5. Okay, now then, because it is from the mean, you go to the right and to the left 1.5 times standard deviation, then the one outside must be less than 1 over 1.5 squared. When I use my calculator, that's approximately 0.44444, or you can say 44.444%. approximately.
Real quick, Professor.
Where'd
you get the 6 from?
This 6 here?
Mm-hmm.
Well, I try to build up that 82. So when I add 12, I get 76. And to reach 82, I need to add another 6.
Okay.
Yeah, I think it's better for us to just use this formula.
Okay.
Yeah, okay. To see how many times, how many standard deviation this 82 above the mean, and how many standard deviation that 46 below the mean.
Okay, gotcha.
Okay, now so what portion of the population is in between? Then the question is what portion is in between? The answer will be more than 100 minus 100% minus 44.444%. Okay, which is 55.556%. More than 55.6%. Okay, now Chebyshev theorem, I think in my test in the past, I only asked that one time. But in the department final, they asked that one time in the last 2 years. Okay. For a lot of instructors, this seems to be not that important. Now, I myself don't see this as important for your level, though. It becomes more important at a much higher level. But for now, I just have the feeling of, okay, what is this Chebyshev theorem? Okay, now, next one is empirical rule. Empirical rule. Empirical rule requires the population, or I think I should say the data. This requires the data. The data needs to be approximately bell-shaped. Okay, so when you draw the histogram, for example, you want the data to be bell-shaped, which means it's getting higher when it gets close to the mean. It gets higher when it gets closer to the mean, and then so it doesn't have to be exactly symmetric. Sorry, like that. This one here. Yeah, this is just approximation. Okay. So let's say it looks like this. Yeah, what we mean by a bell shape is that it gets higher when it toward the middle. The frequency is higher toward the middle, something like this. Okay. Bell shape. When we say bell shape, it's like approximately like this, the shape of the histogram, or basically the distribution. Now, and if it is approximately bell shape, then we can use empirical rule, which says the following. Empirical rule consists of 3 parts. It says the following. First one, approximately 68% of the data is within 1 standard deviation of the mean. So you imagine if I have, this is the mean here, let's say this is the mean, and you go 1 standard deviation to the right and 1 standard deviation to the left. Now, the portion of the data in here, within here, is approximately 68%. Now, approximately 95% of the data, so it is not precisely 95%, it's not precisely 68%, but not going too far from that number, is within 2 standard deviation of the mean. So following the figure we have above, so if this is the mean, you go twice standard deviation to the right, and you go twice standard deviation to the left, then approximately 95% of the data located in this interval. Okay, and then approximately 99 point, I don't remember precisely. Let me see, give me a second. Here we go. The 3 standard deviation one is quite small. Give me a second. Yeah, 99.7. 99.7%. Approximately 99.7% of the data is within 3 standard deviation of the mean. Okay, so from number line wise, if the mean, let's say the mean is here, oops, and you go 3 standard deviation away to the right and 3 standard deviation to the left, then the portion of the data that lies in this interval is approximately 99.7%. Now, the thing is, you're supposed to memorize this number for now, okay? But I don't think I will ever ask this kind of question until much later, when we have a better, how to say it, when we get into what we call confidence interval thing. Okay, but for now, if anybody asks you this question, or if you read this question in the book, then yeah, you do it by memorizing. Okay, now so some little example, a more concrete example. For example, the IQ score of adults is bell-shaped distributed. With mean 100 and standard deviation 15. Now then, when we try to see one standard deviation away from the mean, one standard deviation away from the mean, so the mean is 100. If I go one standard deviation to the right, I add 15, right? I add 15, so that would be the mean plus one standard deviation. That's 100 plus 15, that's 115. And if I go one standard deviation to the left, let me use other color. If I go one standard deviation to the right and one standard deviation to the left. So this is the mean minus one standard deviation. That's 85. So from here we see that according to our empirical rule, according to empirical rule, approximately 68% of population has IQ score between 85 to 115. Then suppose we go 2 standard deviation away from the mean. So I add another 1 standard deviation to the right from that 115, and then subtract another 1 standard deviation to the left of that 85. So what is the number here? Subtract by 85, subtract by 15, I get 70 here. And then if I add another 15, I get 130 here, right? Okay, so according to empirical rule, approximately 95% of population has IQ score between 70 to 130.
So, Professor,
Uh-huh.
those percents you showed us earlier,
Uh-huh.
they're always representing like 2 deviations is always going to be 95%, and then 3 is always going to be 99.7%.
That's right.
Okay.
That's right. According to empirical rule, if the data set is approximately bell-shaped, okay, so this is the requirement. This is the requirement for empirical rule to apply. Not for all type of data. Not for all type of data. It has to be bell-shaped. Now, Chebyshev theorem, however, there's no such restriction. Chebyshev theorem applies to all type of data. It doesn't have to be bell-shaped. Okay, so you will see, even though this empirical rule has the restriction that it has to be approximately bell-shaped, the fact is that in our real life, most informations we get is actually bell-shaped. Most of the time, it's actually a very often. Okay, now the word empirical itself means it comes from, how to say that? It comes from a very large observation. So if you observe not only a big size population, but you apply that to even different situations. Like not only the IQ score, for example, you can apply that to the weight, you can apply that to height, you can apply that to GPA, you can apply that to a lot of other things, income, for example, okay? Then you will see, for example, when we talk about income, it is true that we have a lot of people actually not doing well, right? It is true. And then middle class, we have more, right? And then of course, the richer you are, the less people get rich, right? Okay, so only a few people that rich, and we have a lot more. We have a lot more people not doing well. But when we see that from the income, right, it's actually bell-shaped. It is actually bell-shaped. Okay, so the number of people doing very well, very well there is actually extremely small, extremely small. We have a lot more people, you and me maybe, actually on the lower part of that income curve, right? But still, it's approximately bell-shaped because the middle class people, the middle class is actually quite symmetric here. So we can more or less use empirical rule into the income. Okay, this is true, approximately true in, not 100%. Remember, they use the word approximately, right? So it's approximately true for United States. It's approximately true for Indonesia, where I came from. And it's actually approximately true for most of the country. Okay, now of course for the country where corruption really is super heavy, yes, I agree. America has corruption. Give me a country that has no corruption.
India.
You tell me about it. You know, Indonesia has a very, actually Indonesia's corruption is a lot worse. It's a lot worse. Yeah, but the corruption, how to say it, like one thing that we see from a country with a big corruption is that most people will then, we don't really have this kind of situation though. I really want to draw it. We don't really have this situation, but we may have, if the corruption of that country is super big, so super heavy, then very likely the graph looks like this. In which, for example, this is just illustration, that this part here are people involved in corruption. Okay, maybe instead of like flat down there, counts like this. Okay, so you have some group of people actually involved in corruption. You know, and you see, this is like it's not going down like that, but you have a bump like that. Okay, there's some people involved in corruption. Okay, now this is not supposed to be a record, something I record though, but I just assume that's the case. Okay, if you are in economy, then you try to figure out, see that further. Okay, but I read in one article before that one way to see if corruption is very heavy in a country or in certain area, then you have that kind of shape. You have that kind of shape, like this. Like you have some bump there. Yeah. Okay. But anyway, so this is what we have for early use of mean and standard deviation. I call this early uses because nothing much we can say yet, though. We will use this mean and standard deviation heavily once we get to part 3, inferential statistics. Right now, we are still doing descriptive statistics. Try to describe the population without getting too much into making any conclusion. Okay, that's for the early use of mean and standard deviation. Now, next thing is quartile system. Maybe I open a new tab here. system. Now imagine if your data is written as a rectangle. Okay, now Quartile System separates this data set into 4 parts. It will separate this data set into 4 parts. The reason we call that quartile coming from the word quarter, right? Okay, 1/4. So the whole data set is separated into 4 parts, like we have seen before. Let's say this is the minimum data, this is the maximum data. Now, the guy in the middle is the median. I hope you remember that. So the median separates the whole data set into 2 equal parts. Okay, this is the lower half, and this is the upper half. So when we say, for example, just to remind us, so when we say the median is, if the median is 55,000, it means approximately 50% of population or sample may less than 55,000, and the other half, approximately 50% of the population, makes more than, I'm sorry, yeah, 55K here, more than 55K. Okay, if we say the median is 55,000, then the median implies that's in the middle. Approximately 50% should be, I should say 50%, right? I prefer to use approximately 50% makes less than that, and the other half more than that. Okay, now that's what the median means. Now, quartile system divides the lower half into 2 parts, and the upper half further into 2 parts. Now, then the median, you will see that this guy here, this is the median of lower half. And this is the median of upper half. Okay, notation-wise, the median of the lower half is called Q subscript 1, the first quartile. And the median of the upper half is denoted by Q sub 3, the third quartile. The median itself is known, can be said as the second quartile, but we don't use that notation. We don't use second quartile, we just call it the median. Okay, now, so the first quartile separates the lower 25% and the upper 75%. So when we say, suppose somebody tell you, oh, the first quartile of the income is 20,000. Now it means approximately 25%, approximately 1/4, makes less than 20K, and approximately 75% makes more than 20K. Okay, and suppose the third quartile, let's say, suppose the third quartile is 100K. It means approximately 75% makes less than that. and approximately 25% means more than 100K. Okay, now, so you will see Quartile system separates the data set into 4 equal parts. Okay, into 4 equal parts, and first quartile is the median of the lower half. The third quartile is the median of the upper half. Okay, now that's the basic understanding. Now let's go into details. Now keep in mind that the median is the first quartile is the median of lower half, and the third quartile is the median of the upper half. Okay, now more precise definition. The first quartile that we denote as Q subscript 1 is the median of lower half not including the median. And the third quartile that's Q3 is the median of upper half not including the median. Now, I know that TI-84 has its way to find the first quartile and the third quartile, and but the thing is, so let me write it down. We will do it by hand. In my class, the first and the third quartile will be done by hand. Now, the result that the way we do it will be the same to TI-84. The way we do it will be manually. Okay. It can be done also using TI, either TI-83 or 84. Can be done using other software called Excel, SPSS, that's other stat software, Minitab, and the recent software called R. What is there's another one, SAS, I think. Let me see my reference. And then another one called StatDis. Now, the thing is this. If you use the same data, if you use the same data to all these 7 methods, then the manual method, TI-83-84 method, and SAS method, the software will give you, and StatDis will give you the same result. Excel may give you different result. Minitab and SPSS may give you different result. Now, the way that I take will be the yellow one. Oops. The way we do it will be the yellow one. Okay. Now, so Thomas, SPSS, MITAB, and Excel will give us different result. I'm not sure about R though. I'm not sure about R. But if Excel, SPSS, and MITAB will give us different result, then they are not reliable. That's not really true. That's not really true. The thing is, finding the quartile manually or using TI-83, TI-83, 84 can handle not a lot of data. I think only up to 400. Don't quote me for this one. Basically, the way we do it in this class manually, deal with small number of data, okay? And we can say that TI-83, 84, SAS, and maybe StatsDis also are designed to handle a smaller number of data, okay? While SPSS, as far as I know, is the most powerful statistic analysis software. It's not designed to deal with thousands of data. It is designed to deal with like even millions of data. Okay, so using SPSS to find the first quartile and the third quartile is like using a bazooka to kill an ant. You know, that's overkill. No, you don't use a bazooka to kill a cockroach. Okay, for example. Okay, no. So I'm not saying that SPSS is not usable. No, SPSS is designed, especially SPSS, that's the software I used a long time ago. It is designed to deal with a lot larger data. And when you deal with a lot larger data, the question about the median and the first quartile, the third quartile becomes not really significant. There are a lot more things SPSS is designed to do. Okay, yeah. So my point is this. In my class, I want you to do it this way. This is how you do it in my class. Okay, and telling you other softwares, and some of them may give you different result, is to tell you that even though you use TI-83, 84, you will get the same result, but it may take you too long time because you need to type them one by one. It will take too much time for the first and third quartile question. Okay, now, basically be aware that you may get different results if you use different software, because the algorithm they use to find the median, no, not the median. The median, they all have the same algorithm, but the algorithm they use to find the first quartile and third quartile are different. Okay, now let's see an example. A simple example first. Example 1. Suppose we have this data set. I put them in order right away. 23, 24, 24, 27, 28. Yeah, I put them in order right away. Now then you see that the median is the median is 24, right? This 24 here. Okay, now then the lower half will be the part not including that median. This is what we have for lower half, and this is our upper half. Okay, let me use another color for that. Now then, the first quartile is the median of that yellow part of the lower half. But the median of those only two data will be the midpoint, right? The midpoint of those. So because it is between two numbers, I still have to write it as the way we did the median when it is between two numbers. Okay, so if the median is one of the data, you do not include it in as part of your lower half, you don't include that as part of your upper half. Now, what happens if your median is actually not one of the data? Let's say we have the data set 23, 24, 24, 27, 28, 30. So you see the median will be between these two numbers, right? It's between these two numbers. So the median will be 24 plus 27 over 2, that's 25.5. Right? Now then, what is the lower half? Now the lower half will be the parts less than the median, not including the median. But the median is 25.5. So 24 is not the median. You see that? Okay. And 27 is being used to compute the median, but it is not the median. So that's the lower half, and this blue one is the upper half. Now you tell me then, what is my first quartile in this example here? The first quartile is 24. That's right. This 24. Let me use another color. This 24. Okay, and the third quartile is
28.
28. That's right. Okay. Now, I need to give you a little break, but at the same time, I want you to think about the following question. This was my old test. This was my old test. Hold on. Let me see. This is my test one. Okay, the following are the test one scores from my pre-calculus classes from fall 2019. Consider this as population. So I think I sort it this way. I sort it downward. Okay, and then going this way. Okay, so that's 16.5, then 17, blah blah blah, blah 51.5 to 55, and so on and so forth. So you see that the minimum data is 1, the maximum data is 100.5. Okay. Now, my question is, I would like you to do this during the break. Find the median, first quartile, and the third quartile. Okay. Let's see how many data here. 47. N equals to 47. Okay, together with your break, let's say you do this in 4 minutes and then 5 minutes break. we come back at 9:17. Okay, let's see what we have.
We got coffee and chai.
Okay, depends on my mood. I like that answer. Hey, that's actually a good thing to let's do a little poll later on. Like if we have a little break, what kind of break will you like? Yeah, but let's do it later. That's a good stats problem though. Oh, by the way, can anybody tell me that if we answer this question right, well, during our quick break, what drink do you like? Now, then you will get either coffee, chai, okay, green tea, water, right? Okay, what type of data is that? Is it qualitative or quantitative?
Quantitative. No, never mind.
That's right. That's qualitative. That's right. Okay.
Yeah, okay.
That's qualitative. Okay. Yeah. So the number of drink, of course, is quantitative, right? But I mean, if you do the frequency distribution, when you do the frequency distribution, of course, the frequency will be numbers, right?
Sure.
This will be numbers here, but the guy here will not be numerical. This will be just the type of drinks, right? Okay, and the level of measurements will be this one here will be nominal, right? It's just name. So for example, later on we have let's say drink, and the frequency water. Let's say there are 5 of us, and then coffee. Let's say 8 of us, and then tea.
Chai.
Okay, that's chai is tea, right?
Yeah.
Yeah. Okay, let's put it as tea because there are different type of tea. Let's put them as a tea. Let's say there are 7 tea, and then nothing. Let's say 6 of us. A total of how many? 26. Now then, when I ask you what is the average, when I ask you what's the average, what will your answer be? On average, people will get we can calculate the average. We can calculate the average. Now the thing is the way you think about average is you associate the word average to mean. But that's actually not true. In real life, okay, average refers to measures of central tendency.
Coffee.
Okay, so if because this is nominal level, right? So we refers to the mode.
Coffee.
In this case, is coffee. Okay, I once asked this question in the past. Let me stop sharing this for a while so that you can see my face for a little bit. Okay. I once asked this question in the past. How many? So I asked students from my previous classes. Okay, so I asked them, how many of you actually work in F&B service before, like McDonald's, Burger King, and so on and so forth. And then, oh, I'm sorry, that's right. I go back to sharing. Yeah. And how much pay you get hourly? And then some of them say 9. Okay, well, they say they get 9, but on average, so I have a student say on average people get $9 per hour. Okay, and then I challenge that person not to say that person is wrong. Okay, when I say, when you say your average, were you referring to that you actually add all those people's, your friends, your colleagues, hourly pay, and then divide it? Let's say you have 10 friends, you ask them, you have 10 friends, and then you ask for their incomes per hour. Somebody get 9, somebody get 10, somebody get 8, somebody get 10, somebody get 8, and so on and so forth, and then divide by 10. Is it what you actually do? And she say, no, that's not what I did. You know, so what did you, when you say 9, on average is 9, when you say average is 9, you give me biased data. I mean, you purposely give me biased data. And then she say, well, I'm not trying to give you biased data, right? I said, well, say nothing wrong with what your answer though. When she said that the average is 9, she was not referring to the mean. She was referring to the mode. Okay, when she says that, well, on average, my friends actually get $9 per hour, she was actually asking a lot of people, and then most of the answer she get is actually 9. Okay, so when she said the average was 9, she was not referring to the mean, she was referring to the mode. You see what I mean? Okay, so in algebra, it is true. In algebra, when we say the average, it refers to the mean, but in statistic and admit it or not, in our real life, when we say average, sometimes it refers to the mode. Okay, and we use mode for the measure of central tendency when it comes to nominal data. Okay, now let's come back here then. There's a little use of, don't worry about this. You will not see this kind of question in your department final. Yeah, you will not see this type of question in your department final, so don't worry about it. Okay, let's go back to this, the thing we have here. How do we find the median? Oops. The data set, the population size is 47. So to find the median, 47 plus 1 over 2, that gives me 24. So I need to look for data number 24. 10, 20, 21, 22, 23, 24. That's the median. Okay, now then, how many data in the lower half?
23.
23. So you see the median is exactly this number 58.5, right? It's exactly that one. So the median should be counted from 57.5 down. There are 23 data there. Okay, there are 23 data there. So let me use blue color. 23 data plus 1 divided by 2, that's 12. So data number 12 is the first quartile. Now you will see data number 12 from the top will also be the median of the upper half. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, you can count it from here too if you want, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now then that's how we get the first quartile and the third quartile. You need to do the median first though, okay? Now, if you read further into this chapter 3, you will have something called box plot. Box, is that a whisker? Something looks like this. Something looks like this. Now, if you see this kind of numbers, this kind of diagram, then the number here refers to the minimum. The number here refers to the maximum. This number in the middle here refers to the median. The number here, the first quartile, and the number here, the third quartile. Okay, so let's say, for example, you see something like this. And let's say this is 55, 74, 91, 40, and then 12. Now, if you see something like that, it means the minimum data is 12, the highest data is 91. Actually, you know what? I'm sorry. Let's just use the number we have up there. What is the minimum data from the guy we have up here? So the minimum data is 1. See somebody sending a message. Yeah, the minimum data is 1. The maximum is 100.5. What was the median again? Scroll up a little bit. 58.5. The third quartile is 76, and the first quartile is 20.5. Like that. Okay. Yeah. At least for now, that's how we do it. At least for now, that's how we do it. Now, there's a term called outlier. Outlier. Outlier refers to the data. There are actually two definitions. I'm sorry. Definition, outlier. The first definition, and they may result in different, they may come up with different results. The one being used commonly is the second one. Okay. The first one is, the first one is usual interval is the interval between the first quartile minus 1.5 interquartile range and the third quartile plus 1.5 interquartile range. Now, interquartile range itself means the third quartile minus the first quartile. That's what it means. Okay, so from the information we have above, then our interquartile range will be 76 minus 20.5. What is that? 46.5. Okay, now 1.5 times that interquartile range will be plus 23, that would be 69.75. Okay, so the lower fence which is Q1 minus 1.5 interquartile range is 20.5 minus 46.5. I'm sorry, 69.75. That's a negative number, huh? That's negative 49.25. And upper fence, which is third quartile plus 1.5 interquartile range. That will be 76 plus 69.75. That's 145.75. So the usual interval is the interval between negative 49.25, 145.75. Now, I hope you remember this notation here. Back in intermediate algebra, we call this interval notation. If you don't remember what is interval notation, what do? Google it. Okay? Interval notation. Now, then outlier refers to the data point that is not in usual interval. Okay, but this interval here is way too big. The interval here is way too big. There's 1 is definitely in there, 100.5 also in there, compared with this data here. Okay. So as much as, according to that method, as much as we would like to say, oh, this person is terrible, these two people here is very, very terrible, how can you get only 1 in Thomas test, in any test? Well, for the same reason, you need to say that this person is actually break the curve from above, right? As much as you want to say that these two people or even 3 people try to break the curve from below, then this person also break the curve from above, right? Okay. Now, usually the method that I just showed you to find usual interval and therefore find the outliers here, the first method here, usually being used when the data set is less than 30. Usually used when the n, the sample size, population size is less than 30. Let me use less than 30. Approximation though, this is approximation. Okay, now when the data size is larger, we use this second method. Usual interval is defined to be, and this is what I use by the way, is defined to be the interval within twice standard deviation of the mean. Okay, so if we take a look, for example, this number line here, let's say this is the mean, either mu or x bar. You go twice standard deviation to the right and twice standard deviation to the left. Okay, or if you subtract twice the standard deviation plus twice the standard deviation, let me make an S looks like that so that you don't think of that as a 5. So the mean plus twice standard deviation, the mean minus twice standard deviation. Now that's the usual interval. If it is empirical, if the data set is approximately bell-shaped, then it will contain approximately 95% of the data. Okay, that's the usual interval. So using the data we have earlier, well, we cannot use this yet though, because we don't know the mean, we don't know the standard deviation for this yet. Okay, but we can find that later on. Okay, yeah, we can find that later on. You can find it already, but it's just take longer work. But so suppose out of just for fun, suppose the data, the population above gives the mean equals to, I just make up numbers, okay? I just make up numbers. Let's say the mean is 55 and the standard deviation is, let's say 24, okay? Then the usual interval is, the mu, so let's say mu plus twice standard deviation would be 55 plus 2 times 0.4, that's 48, that's 103. And the mu minus twice standard deviation, that's 55 minus 2 times 0.4, that's 7. So the usual interval is 7 to 103. Then what will the outlier be? Outlier, you compare to the data above. You compare to the data above. Which data here not in that usual interval? Remember, the usual interval is from 7 to 103. From 7 to 103 means from here, including this, right? From 7 to 103. Now, the data that is not in that interval are the outliers. That's the outliers. Okay? Then the outliers are 1, 3, and 3.5. So you see that that's the issue we have earlier. That is it because this person is over prepared for my pre-calculus class, or this person is under prepared for my pre-calculus class? It's kind of hard to decide, right? Okay, if you are somebody who get lower score, you can say, oh, this person is repeating the class. No wonder he's actually doing much better. And it turns out that this 100.5 student is actually a high school student. Never take pre-calculus. See? Okay. So instead of you, this lower group, blaming those people in the other end, okay, and people in the other end bad mounting the people in the lower end, then we use statistic to decide, right? Okay, we use statistic to decide. And the nice thing about this this method is the mean and standard deviations actually coming from your own data. So it's not because of the professor say, oh, you know what, the 1 and 3 are the one not doing well. Okay, and we can tell if the test is too hard or too easy from here. Right? It turns out that the usual interval cover this. Right? Okay, so these people here cannot say my test is too hard because according to our statistic analysis, okay, they are the one outlier. Okay, now I will know that my test is too hard, for example. I know that my test is too hard if, for example, that the usual interval covers these people. Then I have two outliers. Means these two people just perform significantly better than the rest of the class. Okay. Now let's go on further. That's about the quartile system. Now, what is percentile? So the topic here, the topic that I show you here, okay, the first definition of usual interval, and therefore the first definition of outlier, is one of the use of quartile system. Okay, but usually in practice we don't go that far. People just say, oh, the first quartile is 20.5. Then we know that approximately 1/4 of the class actually score less than 20.5. When we say the third quartile is 76, then approximately 1/4 of the class faring or doing better than 76. Okay, that's what it means. But then we can go further into seeing the outlier using this method. Okay, but again, this is usually used when the sample size or population size is less than 30. Now, once you get larger size, for n greater than 30, use this. Now, the thing is our textbook used the first method. Our textbook used the first method, okay? And some other textbook use the second method. Okay, but if you go to higher level, then they will give you these two definitions. How do we define usual interval and outliers? Okay, now how about percentile? Percentile separates the data set into 100 parts. So instead of separating it into 4 parts in percentile, it will separate that into 100 parts. So you can imagine, suppose this is our data set. Okay, then it will break it into 100 parts. Okay, now my question to you is this. If we go back to the quartile system will separate it into 4 parts, right? Now, how many partitions do we need? We need 3 partitions. In other words, for you to be able to cut it into 4 parts, you need to cut it 3 times. These are the 3 partitions. Okay, now then, if I want to create 100 parts, how many times should I cut it to make 100? Yes, 99 parts, 99 partitions. Okay, so you will see the highest one is denoted P99. The lowest one is denoted P1. Okay, P subscript 1 refers to the first percentile. And P70, for example, means 70th percentile. Okay, there is no such thing called P100. Because if it is percentile, then the partition that we use only 99. The highest partition is denoted P99, the 99th percentile. Okay, now, and of course, if you should not tell other people, oh, you know what, I'm in the first percentile in Thomas class. No, that's not to be proud of. Okay, if you say that you are in the first percentile, it means you are here. Okay, you are here. Only 1% of my class score less than you. That's what first percentile mean. Okay, yeah, that's what first percentile mean. Now, while when we say I'm in the 99th percentile, it means 99% approximately 99% of the population scores less than me or at most equal to. Okay, so 70th percentile means approximately 70% of the data is less than P70. Okay, that's what it means. That's what it means. Now I have approximately 15 minutes left, but I have, what else I need to cover? I need to teach you to construct frequency distribution from raw data. So I won't be able to do the last one here. Constructing frequency distribution from raw data. Let me get this again. Give me a sec. Let's say I have this frequency, I have this raw data. How do we construct a frequency distribution from here, from this raw data? The first step, find the range. Find the range. Range is defined to be the maximum minus the minimum. Okay, so in this example here, the range will be 100.5 minus 1, that's 99.5. Okay. Second, find class width. Class width usually denoted by lowercase w. Class width is defined to be the ceiling, actually let me not use ceiling, is the range divided by number of classes. Okay, now this number of classes usually given to you. Like in my class, this will be given. Okay, but usually between 3 to 20. Now we try to keep it approximately, it depends on the number of data though, depends on the number of data, but we try to keep it not too small, usually not 3. With this size, I think we will go to 4 or 5 classes, okay? Now, then round up to usually units, but maybe 1 decimal places or 2 decimal places, depends on the need. Okay, usually we round it to units in this class. And if we round it to units, we use this notation, the ceiling. The ceiling notation is denoted by this. This is the ceiling notation. It looks like bracket. It looks like bracket. It looks like bracket, but without this part, without this part here. No, without this part. Okay. Now, this ceiling notation means you always round up. You don't do regular rounding. You round up. Okay. So suppose for example, we have 92.3. This will be 93. 92.1 still becomes 93. Okay. 92.7 still 93. Okay. Not regular rounding. Not regular rounding. If we do regular rounding, 92.3 becomes 92. 92.1 becomes 92. 92.7 becomes 93. That's if we do regular rounding. Okay, but if we do ceiling, the round up, 92.3 becomes 93. 92.1 becomes 93, 92.7 becomes 93. Okay, now that's the ceiling. Basically, you round it up. Now, suppose in this question, we round to, we go to 5 classes. Suppose we need 5 classes. Then the class width will be 99.5 over 5. Let me make it 4 classes instead. Let me make it 4 classes. So if I divide by 4, that will be 24.875. And because it is ceiling, it becomes 25. Okay, now then we go on the third step. The first class, the lowest class, starts with the minimum value, the minimum data. Okay, so in our frequency distribution, this is the data, this is the frequency. Then we start with the minimum one, which is 1 in this case. Use blue. Start with 1. Now then, this one is the next one is the one you need to be careful. Okay, the next class starts with the minimum data plus class width. So from this one here, the next class, you add the class width. Okay, so that will be 26. And you keep on doing that until you get 4 classes. Plus 25 again. That will be 51. I get a message earlier. Somebody say 99, but 99. Is anything wrong so far? Nothing, right? Okay. And then plus 25 again. If I add 25 again, there will be 76. How far do I need to go, Thomas? Until you have 4 classes, and now you have 4 classes. Right? Now, then the number you get here will be, depends on how you want to round it. Okay, but I think I will make it 25. And this will be 50. This will be 75. And notice that I keep on adding 25 also, right? I keep on adding 25 also. Then this will be 100. But Thomas, our largest data is 100.5, not 100. Our largest data is 100.5, not 100. Now, don't worry about that for now. You later on, I will insert this 100.5 into this set here. Okay, hold on. Do I make a mistake? No, so far no. Yeah, I need to continue on Monday. Or let me just continue right now. Let me just continue now, right now. We will put 100.5 in this class, but I will explain it later on why. Okay, so we get 4 classes now, and then we put the frequency in. Step 5, tally the data. Tally the data set to get the frequency. Tally the data set to get the frequency. So from 0 to 25, how many of the 0 to 25, 0 to 25 here, right? There are 14. From 26 to 50, only 4. 51 to 75, 17. And 76 to 100, including these 2 guys, I get 12. 50.5, we will count it as 51. 50.5, we will count it as 51. Yeah, I will count it as 51. Okay? Yeah, I will count it as 51. So now make sure that after you're done with the tally, you add the frequency, and the frequency is supposed to match with the size of that population or sample. Okay, and when I add these, what do I get? That's 47, right? So that's the same to the population size we have earlier, 47, right? Okay, now, there's something that I need to go on though. Sorry, I have only 3 minutes left, but I need to explain this to you. I have to explain this to you. Some terminology called lower class limit, lower class limit, and upper class limit. Now, lower class limit, give me a second. Lower class limit, oops, no, my bad, no, not this one. Lower class limit refers to this. Now, lower class limit refers to these numbers here. This is lower class limit. Lower class limit refers to this. Upper class limit refers to this. Okay, so if later on I ask you what is lower class limit, then you will say the first class lower class limit is 1, and then 26, and then 51, and then 76. Okay, then upper class limit for each class is, the first one is 25, and then 50, 75, 100. Is it okay so far? Oh, somebody write something there. Erase it, please. Okay, now, next. The one important one to explain is something called a boundary. Lower class boundary and upper class boundary. Now, lower class boundary and upper class boundary refers to the midpoint of that upper class limit, lower class limit. Now, let's take a look on this illustration first. So you see that the classes we have are actually separated this way on the number line. So we have 1 to 25, 26 to 50, 51 to 75, 76 to 100. Is that right? Okay, those are the classes. Now, the boundaries, actually the midpoint between the limits. Okay, so the midpoint between the limits. So this is 25.5. This is 50.5. This is 75.5. Now then, so upper class boundary for the first class. The first class is here. This is the first class, right? Okay, so nominally they say it's between 1 to 25. Normally they say it's between 1 to 25. But then it goes up to here actually. Even though I don't write up to 25.5, okay, but informally, anybody who get 25.4, for example, will be categorized into the first class. Now that boundary is being shared with the next class. Okay, now for the second class, it starts from 25.5 up to 50.5. So lower class boundary for the second class is 25.5. The upper class boundary for that second class is 50.5. Okay, now the third class, lower class boundary 50.5 up to 75.5. And then the last class from 75.5 up to something. Now, what is that thing? Notice that the distance between the limit and the boundary is 0.5. Limit to the boundary 0.5, right? So then using that rules that we use in the middle, we will extend that also 0.5 to the left and 0.5 to the right. Okay, so lower class boundary for the first class will be 0.5. And here it will be 100.5. Okay, now I think I have to stop here, but during this weekend, do the following. Of course, you review the notes that I give you here. Now, once you're done reviewing the notes, try my test 1 problems. From number 1 to number, supposed to be number 9. 1, 2, 3, 4, 5, 6, 7, 8, yeah. Number 1 to number 9. You can start working from winter 14. I think you can find fall 19 also, and others. Okay, all my test 1, starting from winter 14. Starting from winter 14, my test 1. I think even my spring 14 or fall, fall 13, spring 13, you still can use it. Okay, but try to work on at least 3 problems, three test 1, number 1 to number 9. Okay, that actually summarizes whatever I teach you in this 1 week. Okay, that's for today.